My esteemed colleague, Professor Harman, has given me this opportunity to try to explain magnetism to you because it happens to be my area of research. And to begin our discussion, I have to give you some new vocabulary words. And the first vocabulary word is diamagnetic. We say that a substance is diamagnetic when it's repelled by a magnetic field. And the way we'd measure that is with a Faraday balance, among other different methods. So imagine that this system here starts out being exactly in balance, where we put our sample on the right-hand side, and then we offset it with some weight such that this bar is exactly level. And now we bring a magnet up and put it underneath our sample. If the sample tips in the direction shown, in other words, it appears to weigh less in the presence of the magnetic field, we say that the sample is diamagnetic. And furthermore, we can go so far as to say that diamagnetism results from paired electrons. So in other words, all the electrons in the sample are paired up, and when all the electrons are paired up, the sample behaves as though it were diamagnetic. Now, in contrast, a substance is paramagnetic when it does have unpaired electrons. And the way we show that is with the same Faraday balance, except again, it starts out exactly balanced, and now we bring up a magnet, and now the sample appears to weigh more in the presence of a magnetic field rather than when there's no magnetic field there at all. And paramagnetism results from unpaired electrons. So if a sample has unpaired electrons, it's going to be paramagnetic. Well, we've looked at a fair number of compounds and ions that are paramagnetic, or at least we've talked about them. We talked about nitric oxide and how it had an odd number of electrons because you just couldn't satisfy the octet rule, starting with something that had an even number of valence electrons and odd number of valence electrons. Similarly, nitrogen dioxide has an odd electron associated with it, and chlorine dioxide has an odd electron associated with it. Two other species that turn out to have biological relevance, superoxide, which is an oxygen molecule to which we add another electron, and hydroxyl radical, which is hydroxide anion from which we've removed an electron. You can convince yourself that based on Lewis dot structures, neither of these can satisfy the octet rule for all the atoms, and that no matter what, the Lewis dot structure has to have an unpaired electron. Now, we've also talked briefly about dioxygen and how even though Lewis dot structures in valence bond theory don't predict that dioxygen should have an unpaired electron, in fact, two unpaired electrons, molecular orbital theory, which superseded valence bond theory, does adequately explain the result. And the result is, if you take oxygen, it is attracted to a magnetic field. So that's another way you can measure the magnetic properties. You can weigh it, or you can just show that it's attracted to a magnetic field. And typically the way that experiment is done is to take liquid oxygen and pour it between the poles of a strong magnet, and you'll see that it actually sits between the two poles of the magnet. Okay, so now the kinds of compounds that Professor Harman has been telling you about, transition metal compounds, things like cobalt hexafluoride, which is high spin, meaning that the way the electrons fill the d orbitals, you put one in each one of the three lower orbitals, and then you put one in each of the two upper orbitals, and then if you have more electrons left over, you put another one, you start pairing them up. So this species has 4 unpaired electrons. And in contrast, the cobalt hexamine is low spin. It has no unpaired electrons because because the gap is larger here, what you do is you start putting electrons in these 3 orbitals, and then since these are too high in energy, you have to go back and put electrons in the first 3 orbitals that you started with. As a result, cobalt hexamine has only paired electrons, and we say that it would be diamagnetic, whereas hexafluorocobaltate 3- is going to be high spin and paramagnetic, meaning that it will be attracted to a magnetic field. Well, could you have predicted that this should be the case? No, probably not. The point is that by measuring the magnetic properties, we can learn something about the compounds, not the other way around. We use magnetic properties as a tool to measure physical properties about the system, and in particular, we learn that the hexafluorocobaltate is paramagnetic, whereas the hexamine cobalt is diamagnetic. Now, there's another kind of paramagnetism, and that is the one that's associated with unpaired electrons in a metal. So when we were talking about the free electron model of a metal, which was the most rudimentary description, we imagined that the nuclei and the core electrons lived at lattice, and then the valence electrons were just allowed to float around free in the bulk and do whatever they wanted to do. They almost form what we call an electron gas Okay? Not a gas in the conventional sense, but a gas in the sense that they can sort of float around and do wherever they want and go where they want to go, just like gas in a balloon. Well, these represent what should be unpaired electrons. And so there is paramagnetism associated with these unpaired electrons, and that's what we call, in fact, polyparamagnetism. Not really important what it's called, but the idea is that these conduction electrons, the ones that are responsible for making a metal so that it conducts electricity, can also be those that give rise to having the sample being attracted to a metal. But unfortunately, not all metals are paramagnetic. Not all metals are paramagnetic. And so that means that the free electron model can't be the whole story. So here's another place where the free electron model is weak and where we have to use a more sophisticated model, which is band theory, in order to fully explain what's going on. It turns out for really simple metals like lithium, potassium, sodium, which only have one valence electron, everything works great. But as soon as you evolve beyond that into the transition metals and stuff like that, then it starts to break down, and so you have to use band theory in order to explain the magnetic properties. And in particular, band theory also gives us something else. It gives us something called ferromagnetism. And what a ferromagnet is something that is attracted to a magnetic field, but not as weakly as a but much more strongly than a paramagnet. And you know what a ferromagnet is. It's the kinds of things that stick to your refrigerator door. I'm taking a slight liberty with terms here, but something that would stick to your refrigerator door is a ferromagnet. So what distinguishes a ferromagnet from a paramagnet? And in fact, one thing I'll tell you is that a paramagnet, when you cool it down, sometimes becomes a ferromagnet. In other words, when it's in its paramagnetic state, it's attracted to a magnetic field, but as you cool it down, it undergoes a phase transition until it might be really, really attracted to a magnetic field, so much so that a refrigerator would stick to it. Okay? So, how do we understand the distinction? And the answer is that you can imagine that a paramagnet consists of a bunch of little bar magnets. So the unpaired electrons in the paramagnet behave as though they're little bar magnets. And what happens when you take this sample and you apply a really large magnetic field is all the little bar magnets line up with the applied magnetic field. But when you take that applied magnetic field away, what happens in a paramagnet is the unpaired electrons go back to being somewhat random. They don't no longer have all their little bar magnet norths pointed in one direction and all their bar magnet souths pointed in the other direction. Whereas if you take something that's a ferromagnet, okay, and if you heat it up, remember I said that if you heat up a ferromagnet, it becomes a paramagnet, okay? So if we imagine that this is the ferromagnet at really high temperature, and we put it in a magnetic field, and then we take away the magnetic field, it stays aligned. And so a ferromagnet stays aligned when you take the magnetic field away, whereas a paramagnet, when you take the magnetic field away, goes back to being random. Why? Well, the reason is that there's an interaction between the unpaired electrons that makes them want to point in the same direction. Right? And so when one of them points in a direction, the next guy wants to point in that same direction, and the next guy, and the next guy, and the next guy, and so they stay aligned. Here's an analogy. Suppose we take 12 people, okay, 12 little spins, and they don't know each other, and somebody says, well, let's go to the movies. Well, some of them might go to the movies and some of them might not go to the movies. But if we took 12 friends who really liked each other and one of them said, let's go to the movies, they'd all go to the movies. So the idea is that because there's an interaction that makes these guys want to line up with each other, this thing stays magnetic whereas when you remove the magnetic field, whereas this thing doesn't. Now, to illustrate that idea, what I'm going to do is take a paper clip, actually 2 paper clips, okay, and show you that these 2 paper clips are not attracted to each other. So these paper clips turn out to be ferromagnets, but in the totally random state. So these are ferromagnets that are totally randomized. And now I'm going to align them by putting them in a big magnetic field, and this is a big magnetic field. Okay? So we put them in this big magnetic field, and now all of the spins are doing what's going on here. And now I'm going to take away the big magnetic field, okay? And now I'm going to show you that they get stuck in this aligned state. And the way you can tell is they stick to each other now. Okay? So each one of these now has become a little tiny magnet, and you know that magnets like to attract each other north to south, and so what happens is now the unpaired electrons in the little paperclip are attracted to each other, and so we have made new magnets from things that weren't magnets before. All right, so obviously, or you'll have to take it on faith that I've cut a lot of corners and I've been a little liberal with terminology, but the idea is that unpaired electrons are what give rise to interesting magnetic properties, that if you have unpaired electrons, then the thing is paramagnetic. If there are interactions between the unpaired electrons and if they're strong enough, the thing is going to be ferromagnetic. And then if you have only paired electrons, then the substance is diamagnetic. And this is just a way that we can organize stuff in our world, just like the way we're trying to organize things in terms of solids and liquids and gases and stuff like that.